All right, welcome everyone. So today we're going to be talking about the test for divergence. So we've kind of moving into our new unit of material here. So we've talked about sequences, we've talked about series, and now we're going to be looking at kind of a bunch of different tests that we can use to kind of quickly determine whether a series is convergent or divergent. And so the first one we're going to be looking at, we call the test for divergence. All right, so let's kind of see the motivation here. So what's the motivation for this new unit? So we're usually interested in calculating the sum of a series, but unfortunately, usually calculating that sum is very difficult. So getting an exact value is very difficult. And so usually the best we can do is to say the series is convergent, so the sum actually exists. We won't necessarily know what the sum is exactly. We'll just know that it exists. The series is convergent. Or it's helpful to know if our series is divergent. The sum does not exist. So usually this is the best we can say. Either our series converges or it diverges. And so we're going to be developing all these different tests that allow us to quickly say, given a series, is it convergent or is it divergent? And so again, the first one we're looking at is the test for divergence. And we can use this test to show whether or not a series is divergent. It's a fitting name. All right, so let's look at it. So what does the test actually say? So let's suppose we have a series, sigma an. We calculate the limit of our original sequence an. So we're doing the limit of our original sequence an as n goes to infinity. And the test for divergence really comes down to the value of this limit. So if the limit does not equal 0, or the limit does not exist, then our series is divergent. If the limit of an does exist, but it's equal to 0, then unfortunately this test is inconclusive. We just don't have enough information to say what happens with our series. It might converge, it might diverge, we just don't know. The test is inconclusive. All right, so let's kind of just look at this again. So the limit that we're doing here, the limit of an, this is just our original sequence that we're doing the limit of. Just our original sequence an. We're doing the limit of it as n goes to infinity. And so what this test says, there's kind of three different cases here. If the limit of an as n goes to infinity does not exist, well then what this says is that our series sigma an is divergent. The other option is if the limit of an as n goes to infinity does not equal 0, well, same thing. Our series is divergent. And if the limit of an does equal 0, well, then the test is inconclusive. And what that means is we just don't know. We don't have enough information. So that the series might converge, it might diverge, we just don't know. We don't have enough information. So normally what we would do is if we got this inconclusive result, we would go on and try some other test. Now a common mistake, so there's a warning here which we'll look at in a second, but a common mistake is if we do the limit of an as n goes to infinity and we get 0, this does not mean all right, so if we do the limit of an and we get 0, Again, the test is inconclusive, but it's a very common mistake to say, all right, if the limit of an is equal to 0, well, then my series sigma an must converge. It's not true. So if the limit of an is equal to 0, that does not mean the series necessarily converges. We just don't know. The test is inconclusive. So to put this another way, the test for divergence cannot be used to show that a series is convergent. So it only can be used to show that a series is divergent. So if we go through the results again, if the limit of an does not exist or the limit of an does not equal to 0, well then our series sigma an diverges. And the only other case is when the limit of an is equal to 0, but the test is inconclusive. So if the limit of an does equal 0, what that actually is telling us is it tells us the original sequence an, that converges. That's converging to 0, but it does not tell us anything about what our series sigma an is doing. We just don't know. So normally we would go on and try some different test to try something else. All right. So let's just think about why this test kind of works. So we'll look at a kind of an intuitive proof for why this test for divergence makes sense. So let's suppose that the limit of our sequence an as n goes to infinity is equal to some number L which is greater than 0. So we're supposing that the limit of an does not equal 0. It's actually equal to some number that's bigger than 0. So the case where L is negative would be similar. And we can graphically think of our sequence as being points on the number line. So we're looking at the positive case. So let's just graph the positive portion of the number line. And we have our limit here, which we're calling L. So it's bigger than 0 in this little kind of illustration. And so what happens when a sequence gets closer and closer to a number is if we were to draw an interval surrounding that number L, surrounding our limit, what happens is that eventually all of the terms of our sequence fall inside that interval. So eventually, so there might be a few terms towards the beginning of our sequence that fall outside this interval, and that's okay. But eventually, if we go far enough into our sequence, eventually all of the terms do end up inside here. So they're close to this number L. And so the idea is that we can choose this interval. We can choose any interval here. And so eventually, any interval we choose, eventually we go far enough into our sequence, all of the terms fit inside that interval. And so we can choose the interval where L over 2, the kind of the halfway point between 0 and L, we can choose that so it's one of the endpoints of this interval. And so what this means then at some index n, if we go far enough into our sequence, at some index n, all of the terms of our sequence are greater than this endpoint, L over 2. So if we go far enough into our sequence, there's some index n where once we get beyond that point, all of the terms beyond that point are greater than this endpoint, L over 2. So they fit inside this interval. And so what that means for our series then is when we actually go to calculate sigma an, what happens is essentially we're trying to add up an infinite amount of numbers that are greater than L over 2. So we're attempting to add more and more copies of numbers greater than L over 2. That's what we're trying to do. When we calculate the series, we're trying to essentially add more and more numbers, not even copies of numbers, just more and more numbers that are greater than L over 2. And so what happens is the sequence of partial sums just keeps getting bigger and bigger. So this is just kind of showing us that if we go far enough into our sequence, eventually all of the terms of our sequence are inside this interval. So eventually most of the terms then are bigger than L over 2. And what happens when we add up more and more copies of L over 2? Well, the sum gets progressively bigger and bigger, and it goes to infinity. And so the sequence of partial sums is getting bigger and bigger, means it diverges. And so that means our series diverges as well. So it's just a little illustration to kind of help you kind of conceptually think what's happening if the limit does not equal 0. Well, if the limit does not equal 0, then you can find this kind of space here. And then eventually, when you're trying to do the series, you're attempting to add up an infinite amount of numbers that are greater than L over 2. And so the sequence of partial sums just gets bigger and bigger. So the series diverges. All right, so how do we actually use this test for divergence? Let's try a couple examples. Example 1. We're going to determine if this series is convergent or divergent. So it's the series sigma n equals 1 to infinity of n squared over 3n squared plus 1. And what we're going to do is we're going to start off trying to do the test for divergence. So what do? Well, we calculate the limit of just this original sequence. And we're doing the limit as n goes to infinity. All right, so let's see what happens with this. We're going to use our standard, it's a rational looking expression here. So we're going to use our standard 1 over n trick. So we identify the largest power of n in the denominator, and we essentially divide each term by that largest power. Or another way to think of it is we multiply both the top and the bottom by 1 over, in this case, n squared. That's our largest power of n in the denominator. So when we distribute that in our numerator, what do we get? Well, we get 1. In the denominator, what do we get when we distribute? We get 3 plus 1 over n squared. And then if we do the limit of this as n goes to infinity, these fractions, this fraction 1 over n squared, that's one of our c over infinity forms. So this goes to 0. So we end up with 1 over 3 plus 0, which is 1/3. And so what we're seeing here is the limit of an as n goes to infinity is equal to 1/3, which does not equal 0. So the series diverges. All right, so actually let's write this up here because we want to, when we do these, we want to get into the habit of providing some justification. So what we've shown here is that the limit of an is equal to 1/3. And we're saying since the limit of an as n goes to infinity is equal to 1/3, which does not equal 0, the series diverges, and we just want to state which test we're using. And I mean, we kind of stated it here, but it's good practice to just, it's a good habit to get into of just kind of writing out a nice kind of written statement here. So we're going to say the series diverges by the test for divergence. So we want to state the test that we're using. And that's really it. So we're just showing our work for calculating the limit of an. We see that we get a non-zero value, which automatically means the series diverges. All right. Let's try another one. Let's look at example 2. So we have a series here, and we're going to determine if it's convergent or divergent, and it's the series sigma n equals 1 to infinity of 1 over n. So let's see what happens when we try the test for divergence. So we're going to calculate the limit of an as n goes to infinity, and that's just the limit of our just original sequence, so 1 over n. And we're doing the limit as n goes to infinity. And again, that's just one of our c over infinity forms, so the limit is 0. So what that means is when we do the limit of an and we get 0, the test for divergence is inconclusive. So we have to stop. Doesn't tell us anything. So the test is inconclusive. The test for divergence doesn't actually tell us anything about this series. So yes, the sequence formed from 1 over n, the sequence, the original sequence, that converges to 0, but we're not interested necessarily in just that sequence. We're actually interested in the series. What is the series where we're attempting to add all those terms together? What does the series do? And so we have to try something else. And so the something else in this case is to recognize that this is actually a p-series. So this is a p-series with p equal to 1. And if we remember back, a p-series diverges when the p-values are less than or equal to 1. So this is a p-series. Sometimes we also call this one a harmonic series when it's the special case when p is equal to 1. But this is a p-series with p equal to 1, which diverges because our p-value is less than or equal to 1. And so this is a divergent series. But the test for divergence did not tell us that. The test for divergence was inconclusive. All right, let's try another one. Good to practice these. All right, here we go. Another p-series. So we can quickly say whether this is going to converge or diverge, but let's see what happens with our test for divergence. So we're going to determine if this series is convergent or divergent. It's the series, the sum from n equals 1 to infinity of 1 over n squared. Let's try out our test for divergence. So we're going to do the limit of our sequence, an, as n goes to infinity. And that's just the limit of 1 over n squared as n goes to infinity. We're doing the limit of that. Again, that's just a c over infinity form, so the limit is 0. And as soon as we get that the limit of just our original sequence an is equal to 0, we have to stop with this. The test for divergence doesn't tell us what's happening with our series. So the test is inconclusive. So our test for divergence doesn't tell us what's happening to this series. All we get is this inconclusive result. All right, so we have to try something else. And fortunately, like we said, this is a p-series. So this is a p-series. And what is the p-value? Well, p is equal to 2. It's just the power of it's the power function here. And our power here is 2 for our denominator term. And when our p-value is greater than 1, our p-series then is convergent. So we're just kind of providing some justification. And for a p-series, this is enough justification. We're identifying that it is a p-series. We've stated the actual p-value. In this case, p is equal to 2. And then we're stating the result. It's convergent, and that's because our p-value here is greater than 1. All right, so if we compare the results between example 2 and example 3, in example 3, we had this convergent p-series, but the test for divergence was inconclusive. And we calculated the limit of a and we got 0. Test for divergence was inconclusive. In example 2, what do we see in example 2? Well, something similar. The test for divergence, we did the limit of an, we got 0. The test for divergence was inconclusive. But here, we had a divergent p-series. So when we do the test for divergence, when the test is inconclusive, it means we don't know. We don't have enough information just by using the test for divergence. We have to try something else. So in examples 2 and 3, that something else is, well, we identified it was a p-series, and so we were able to say what happened from there. But the test for divergence, the fact that the limit of an was 0, is inconclusive. Doesn't give us enough information. All right. So this is a nice quick test that we'll be able to kind of refer back to from time to time. Next time, we're going to kind of keep going with this, and we're going to look at another test, which will kind of allow us to say a little bit more. So we'll kind of keep building on these ideas of testing series for convergence or divergence. But this is a good one to kind of get us started. All right, so we'll see you then. Bye-bye.